All right, hello everyone. Making a quick video going over some example FRQs that should be very useful for the test. So let's just hop right to it. So the first problem, I already have the first part written down, and we'll go over it in detail. So let's imagine that we're racing in the Indy 500. Okay, so for those who don't know, the Indy 500, it's a 500-mile race, 200 laps, and each lap is 2.5 miles. All right, now let's say we complete it in 3 hours. All right, so one question could be, what's the average speed of the car, right? So if you complete the Indy 500 in 3 hours, what was your average speed? So here I have average speed is distance over time. Ignore the little red underline thing. I'm not sure why the iPad does that, but it'll go away eventually. So anyways, we know average speed is distance over time, and we get 500 miles. That's the distance traveled over 3 hours. You end up with an average speed of 167 miles per hour. All right, so simple enough. Now, if I were to ask a slightly different question, say I were to ask you about the average velocity. Okay, the average velocity. Well, average velocity, technically that's different from average speed, although they're very similar. So velocity is a vector, speed is a scalar, and velocity is defined as the displacement over time. So the average velocity is going to be equal to the displacement over time. Okay, so here's the deal. The Indy 500 is on a circular track, right? So if you think about a circular track, here I'll draw a circular track as best I can here. All right, so let's pretend this is the track for the Indy 500, and you just go around and around in a circle. So if my starting position is here, okay, and I complete my 200 laps, all right, I'm going to end up at the finish line when I'm done with the race. That's going to be my final position. All right, so let's assume we stop measuring. As soon as I cross the finish line, that's the end of the motion, right? So at that point in time, what's the average velocity for the whole trip? Well, since the final position is going to equal the initial position, right, because I'm going around in a circle, we know displacement, right, is going to be delta x, my change in position, so xf minus x naught, but we just established that they're at the same position, right? So if I call this position 0, then xf is also 0, right? And my displacement is going to be 0. All right, so 0 displacement. So even though I traveled 500 miles, my final position ends up being the same as my initial position. All right, so then the average velocity is actually 0. So the average velocity is 0. I end up right where I started. So I have an average speed of 167 and average velocity is 0. All right, so let's move on to another example. So another example would be, say I were to give you a position time graph. Okay, so here's a position time graph, and you have to plot the velocity time graph. All right, simple enough. If you have an example that's very straightforward, say, here, let me use different colors to make it a little more easy to identify. Let's see, no, that's not it. There we go. All right, for some reason, okay, there we go. So I'm put this down here. All right, so let's say that I have a position time graph that looks like this, okay? Well, we know that the slope of position time graph is velocity. So the slope of position time graph is velocity. All right, so here I have a line that has a positive slope, is going up and to the right, and that slope doesn't change because that's how lines work. They have a constant slope. So if I were to sketch the velocity time graph that corresponds to this position time graph, well, then it'll just be a horizontal line. So I have some horizontal line, right, that corresponds to some positive value for the velocity, right? So whatever that slope is, you know, it doesn't change, so it's just a constant. Now let's imagine I have a slightly different situation. Okay, let's say that the position time graph, say it looks something like this. Let me do one. I'm trying to think how I want to do it. I'll do it like this. Say I do it like this. Okay, so here it's a little different. It's not a line, it's a curve. Okay, so one way you can think about this situation is, imagine you take, let me use a different color here. So imagine I look at the slope at individual points. All right, so I know this seems odd, but one way to think of a curve is a line that's changing slope. Okay, so I look at this curve, I see that the slope of the line is actually negative because it's going down and to the left. I'm sorry, down and to the right. So it has a negative slope, and the slope is slightly negative, but it becomes more negative over time, right? So the slope starts off as slightly negative, and then it becomes more and more negative. So the way I would represent that on my velocity time graph is, well, it's going to be negative, and its value is going to be decreasing in the sense that it's becoming more negative. All right, so you'll see what I mean. So right now, let's hypothetically say the slope here is -1/2. All right, and then here the slope is -1, and then here the slope is -2. All right, so my slope is going to be decreasing, and you should see a plot that looks something like this. All right, and again, we're just sketching here, but it's just the idea that you can have, you're measuring the slope of a curve, okay, at different points, and you see that it's changing, and that's one way to think of a curve. All right, so here's two examples. When it's just a line, it's very straightforward. It's going to be a constant value. And then the same thing for if you have a curve like this, where you just see how the slope changes. I know I start off slightly negative, right? And it becomes more and more negative. And here's a rough sketch of what that looks like. All right, it doesn't have to be perfect. I just need a sketch. Just so we really understand the idea of velocity being the slope of a position time graph. All right, let's do another example. Let's say, all right, so here, let's say I got a graph here. All right, so here's the third example. And I'm just going to go through this kind of quick, so excuse if I don't have the graphs like perfect, but we should be able to get the main idea. So let's say I have a person moving like this. So I'm drawing a position time graph. I'm going to draw two different people. All right, so let me make my axes here. So this is going to be my position in meters. Here's my time in seconds. Okay. And let's say 1, 2, 3, 4. All right, very good. And then let's see, 5, 10, 15, 20. All right, let's say this is a situation. And the person I'm looking at is, let's do the first person, is going to have a graph that looks like this. Let's see here. So, all right, close enough. So I'm going to draw a straight line through all these points the best I can. And let's call this line, this is going to be Alice. All right, this is a graph of Alice's motion. And let's say I have another person that at t equals 2 seconds, they start moving. All right, so t equals 2 seconds. And then let's say I want them to go, how quickly? Trying to see how I want. All right, I got it. All right, I'm gonna make it work like this. So I need to extend this axis a little bit. So I want the numbers to be nice and neat. So I'm kind of designing the problem in a particular way, just so it's like, you know, obvious. Yeah, let's get to it. So that's my situation. This person starts here, and let's say they go all the way up here. Okay. And here's the line that describes that motion. All right, let's call this line, this is a line that represents Bob. Okay, so I have two different motion graphs here, one of Alice, one of Bob. Okay, so the first question, all right, so how long has Alice been moving when Bob started moving? All right, so let's write that out. So how long has Alice been moving when Bob started to move? Or I should say, started his motion. All right, so this is kind of a freebie, because all you're doing is just reading the graph. So you look at the graph, I see the line for Alice. She starts at t equals 0, and she's moving as such. And then here's Bob, he starts at t equals 2. So the question is, well, how long has Alice been moving? Well, she's been moving since t equals 0. So she's been moving from t equals 0, okay, So at t equals 2 seconds, well, she's been moving for 2 seconds. All right, simple as that. All right, another part. All right, so this is just reading the graph. So at what position does Bob cross Alice? Bob cross Alice. Right, so at what point does Bob overtake? Because Bob's obviously traveling faster than Alice. He's covering more distance over time. Right, he's moving faster, and the slope of the line is greater, and we know that slope of position time graph's velocity. Right, so at what position does Bob cross Alice? Well, you just look at the graph, and my drawing's a little crude, okay, but it's gonna be a little bit more obvious for the test. So here, what I was trying to do is have it set at 15 meters. All right, so it's not perfect in the picture, but that's what I was going for. So at 15 meters, that's where they cross, right? So let's see, what's the difference in position at t equals 4 seconds? What is the difference in position at t equals 4 seconds? So at t equals 3 seconds, that's when they cross, right? And Bob overtakes Alice, and he's going faster. So what I'm asking about in this problem is, well, I look at t equals 4 seconds. This is t equals 4 seconds. So what's this distance here? All right, well, I see that Alice is at roughly 20. So Alice at position 20 meters at t equals 4. And then Bob is at position 30 at t equals 4. Oops, I said 4 equals. T equals. All right, t equals 4. Okay, so the difference between the two, well, it's just 20 minus 30. So let's just do this. So 30 minus 20. So 10 meters. Bob is 10 meters ahead of Alice. Okay, and that's the basic idea. All right, so here, I'll box that. That's how you do that kind of problem. So far, so good. Now things get a little bit more complicated. Now let's ask a question where you have to actually think a bit. So let's write down an equation of motion. So we're going to write down an equation of motion for Bob and Alice. Or I should say for Bob and for Alice, right? So two different equations of motion. There's going to be two equations that represent their motion. So we did this in some of the labs. We plotted the data in Google Sheets, and we used the function to write out as an equation. But I know you've done this in algebra class. Okay, so if I have a line and I have some data points on a line, I need to be able to determine the equation of the line, right? So we know the equation of a line in algebra is y equals mx plus b. Okay, so m is the slope, b is the y-intercept. Now, in physics, with a position time diagram, this is x in meters, this is t in seconds, all right? So the equation's a little different. This is math, all right? And in physics, if we're dealing with an equation of motion on a motion diagram, on a position time diagram, we're representing the position x is equal to the velocity v, and the reason why it's velocity is because we talked about how velocity is the slope of a position time graph, times t, right? So instead of x, we have t, okay? Plus, now what would the y-intercept be in this case? What's the analogy? The analogy would be x naught, right? So x naught is the initial position at time equals 0, all right? So it's going to have this form. So v times t plus x naught. Now, if you think about it, this comes from the velocity equation. This is just a velocity equation rewritten. Because look, velocity is change in position. Oops, let me redraw that. So it's just delta x over delta t. All right, and we only really care about the motion from t equals 0, right? So our t naught is going to be 0, right? And then delta t is just going to be tf, right? Because delta t is tf minus t naught. All right, so this is 0, so then it's just tf. Okay, so anyways, and a t is changing, right? So we're evaluating as a variable. So basically, if I rearrange this equation here, I have delta x is equal to v times t, okay? T naught's going to be 0, so we don't have to write delta t. And we know that delta x is also equal to xf minus x naught, right? So if I just rearrange the equation, xf minus x naught is equal to v times t, okay? Then xf is equal to v times t plus x naught. And that's like the equation of the line that's going to be represented by constant velocity motion, right? So we're graphing a line. We're not dealing with acceleration. We're just looking at a linear function, all right? So let's actually set up the numbers. Let's do Alice first, because that's easier. Okay, so this is Alice. What's the equation of motion that describes this line? Okay, how do I write this line in terms of an equation? Well, if you did y equals mx plus b, you know the slope. Just look at the slope, look at 2 points on the line. I know it goes from 0 to 20. That's the rise. The run is 4. So the slope is going to be 5. All right, so the slope is equal to 5, right, which is equal to the velocity by definition. All right, and now what's x naught? X naught is going to be 0. Okay, so if I write the equation of the line, I have x, okay, is equal to 5 times t plus 0. All right, so that's the equation. So it's just like in math class, right? Imagine you had an equation of a line that looked like this, right? So you have y, you have x, and it's the same idea, right? 5, 10, whatever, you get the idea. 1, 2, 1, 2. All right, I had these 2 points. I draw a line, right? This equation in terms of y equals mx plus b, the b would be 0, right? Because at x equals 0, y is 0, and you'd have the equation y equals 5x, right? So I know you did that in algebra class, y equals 5x. And in physics, it's going to look like this, x equals 5t. All right, that's the equation for Alice. Now for Bob, let's look at Bob. So again, same deal. We need to figure out what the slope is. So the slope is his velocity. So the slope here, I see that it goes from 2 to 15 in 1 second, okay? And then from 15 to 30 in the next second, right? So I have a rise of 30 over a run of 2, okay? So in this case for Bob, the slope is equal to 15, all right? And that's the velocity, 15 meters per second. Again, I apologize for all these odd lines. I'm not sure. If anyone knows why the Apple Notes app does this and how to fix it, please let me know, because it's very frustrating, but that's how it is, all right? So just ignore it for now. So slope is velocity. The slope of the position time graphs the velocity, and we have 15. Now here's the deal. So x naught, this seems like a bit much because he doesn't start moving till t equals 2 seconds, all right? But there has to be some x naught that's represented by this graph. So here's how I want you to think about it. All right, so imagine, so even though this isn't what physically happened, we're just describing the equation for the line. All right, so we know that t equals 2 seconds, okay? Bob, that's when Bob starts moving, okay? And then at t equals 3 seconds, he's at 15 meters, right? So that's another data point. Now, the question to ask is, at what point is he going to hit the vertical axis, all right? So if you think about it, if he's traveling 15 meters per second, at t equals 0, assuming he started at the same time as Alice, he would be at position negative 30. All right, so let's draw a line that goes through these points, and then here would be at position 1, here's position 2, 3, okay. Or I'm sorry, the time. So at t equals 0, he'd be here, here, and here. Okay, so now this is describing Bob's motion. So you can write out the equation with this y-intercept. And let me give a physical interpretation, right? So the equation of this line, so imagine instead of x and t, it was y and x, right? If it was y and x, you would immediately solve the equation. You know it's 15x minus 30. That's the equation of the line. So it's the same idea with a xt diagram, right? So instead of y, we put x, and instead of x, we put t. So we would have x is equal to 15t minus 30, okay? Now, Bob didn't start moving until t equals 2 seconds, but for the purposes of being able to work with these equations, we can just assume that he did, right? We're just going to continue. We're going to extend that line down with the same slope and see what the y-intercept is, okay? And let's just leave it at that. If you want to get fancy, okay, you could say that, you know, the system of equation would be x equals 0 when t is less than 2. I guess all motion starts at t equals 0. And then you can write this, 15t minus 30 for values t greater than or equal to 2, right? Because it doesn't start moving until t equals 2. But don't do that. All right, so that's what's physically happening. Just write the equation on the line, and you're going to use that to solve the problems, all right? So we know that slope's 15. The x naught, or the y-intercept, in this case, right, you can say x is equal to 15t minus 30. So again, how did I find this? How did I find that minus 30 part? I extended the line here, all right? I extended the line here from t equals 2 to t equals 0, even though he wasn't physically moving. It wasn't that he kept at a constant velocity. We're just going to do that for the purposes of writing an equation that represents this line, right? So we care about this line here, okay? So basically all I'm doing is I'm extending this line out so I can work with the equations, all right? And so these are the equations of motion. Now, when you have it set up as an equation, we can actually work with it, right? So these are the equations of motion for Bob and Alice. That's Alice's equation. This is Bob's equation. Now, finally, let's actually use the equations. So let's determine mathematically where they cross. And then you can check with the graph. So check result with graph. All right, so we're not getting the information directly from the graph. We're going to solve for it using these equations of motion. And I know, as you all know from algebra, if I have two equations, two separate equations, all right, these equations have two variables, x and t, I can set them equal to each other, right? If I want to find a point where these two lines meet, okay, I can set them equal to each other, right? Where, you know, I have, you know, they're going to have the same x coordinate, right? They're going to meet at a point where the x value is the same, right? And same was true with the t value. So you can just set these equations equal to each other. You can use elimination. You can use substitution, however you want to think of it. All right, so the way I'm going to think of it, I'm going to use substitution, right? X is 5t. I have x over here, so I'm going to substitute that in. So I have 5t is equal to 15t minus 30. And we're going to calculate at what point in time do they meet. All right, so solving this equation, you know, all right, so let's say I subtract 15 from both sides. I end up with negative 10t is equal to negative 30. Divide both sides by negative 10. I get t is equal to 3. So at 3 seconds is when they meet. And then what I can do is I can plug that into the original equation, either one, it doesn't matter, to figure out what the x value is. So I know the t value when they meet is 3 seconds. To figure out the x value, I'm just going to substitute that into the first equation. So 5 times 3. All right, and I get 15 meters. All right, and so let me check the result with the graph. Do they meet at 15 meters at t equals 3 seconds? Yes, they do. Right, 15 meters t equals 3. But I didn't even have to have a graph. I could have done that by having this system of equations. Right, so I have two equations for two different types of motion. They're going to meet at some point. Right, you have two different lines with two different slopes on the same plane. There's going to be a point where they meet if you extend the lines out infinitely. All right, so that's the answer. So at 15 meters, so when x equals 15 and t equals 3 seconds, that's when they meet. All right. So let's do a couple more examples, and then that will be it. So next example, actually, let me do something real quick. I'm going to type. So this gets a little laggy as it continues. I'm going to put a little space here. All right, so continued. Okay. So this is going to make it a little bit more stable. All right, anyways, let's do 4. So another FRQ, just to make sure we're prepared. And again, these FRQs, they're going to be in the same kind of style, but obviously it's going to be slightly different, and the numbers I'm working with are going to be easier just so I can explain it more quickly. All right. But these are the kind of problems you want to think about before you approach the test. So let's say I have some data. All right, let's say I have some motion data. Okay, so I'm going to come up with some data here at t equals 0. We did a lab on this, right? So we did a lab with the constant velocity, right? So the constant motion, where we had the little remote control cars. So this is kind of similar. So let's say we're going to look at each point in time, t equals 1, t equals 2, t equals 3. And let's keep the numbers nice and neat. So let's say that, so this is meters, this is seconds. Okay, so at t equals 1 second, it's 2 meters per second. I'm sorry, 2 meters. At t equals 2, let's say the object's at 4 meters, and at t equals 3, the object's at 6 meters. All right, so we can plot that real quick. All right, so 1, 2, 3. Here's time. Here's position. All right, 2, 4, 6. All right, let's just do it like that. So you have 1, 2, 3. All right, let's plot these points. Here, I'll use a different color to make it easier to see. All right, there's first data point, second data point, third data point. All right, there we go. Okay, so now let's say, so this would be one part, like plot the data. All right, so part A, plot data. All right, so I know you know how to make a graph, plot the data, draw a line, a best fit. All right, so there you go, that's A. We plotted the data. All right, another question we could ask. What's the average velocity? So what's the average velocity? Well, again, average velocity, V average, is equal to displacement over time, delta x over delta t. We know that's going to be, let's look at the whole range of motion. Right, so we know it travels 6 meters over 3 seconds. Okay, that's going to be 2 meters per second. All right, there's the average velocity. Simple enough. And let's say, all right, so let's add to this. All right, so let's say it returns back. So this cart returns back to origin. Or I should say original position, okay? So it turns back to original position in, let's say, 12 seconds. All right, so it took 3 seconds to get to 6 meters, and I don't know, so it ran out of batteries. All right, so it takes a long time for it to come back. All right, I'm just coming up with some random example, but the idea is what's important. So it returns back to its original position in 12 seconds. What would be the average velocity on the return trip? Okay, what is V average on return trip? Well, for the return trip, we know that XF is going to be 0. The final position is going to be 0 because we're going back to the original position. And the initial position was at 6 meters, right? Because we're turning back around. We went out to 6 meters. We're coming back around. So my delta X is actually going to be 0 minus 6. That's negative 6. My displacement's negative 6 meters. All right, my time is 12 seconds. All right, so then we'll just do the math. V average, I have negative 6 meters, right? That's my displacement, and that happens over 12 seconds. So my average velocity is negative 0.5 meters per second. Now for this, it's critical that it's negative, right? We're returning back to our original position, right? If I extend this line out, let me kind of extend this out a bit, and it's going to go all the way out to x equals 12, right? So, you know, I'll just draw it. Actually, it's going to have a smaller slope than that. Let's see here. Well, anyways, you get the idea. Okay, so it's slowly going to go back. Okay, and I'm going to erase that for now, but you get the concept. So it goes back to its to the position x equals 0, and that takes an additional 12 seconds for it to do that. All right. So on the return trip, the velocity is going to be negative 5, right? Because it travels 6 meters, but it takes 12 seconds to do that. All right, so that's one example. Applying some data, getting information from the graph that you plotted, and being able to use that information. Okay, so finally, let's do one last example, and that'll be it. Okay, and then obviously you should read through your notes, look at your old assignments, whatever topic you don't feel super comfortable with, definitely review that, and you should be fine for the test. All right, so let's do another example from the Uniform Motion Lab. So actually, I'll just go straight over the example. All right, so let's say, from the Uniform Motion Lab, we have, I'm trying to see how I want to do it. All right, I'll do this actually. So I want to involve some conversions. All right, so say I plot centimeters, not meters, centimeters. So centimeters versus seconds. Okay, and then we go from 0 to 10 seconds. All right, I'm going through this quickly, but you get the idea. So let's say the car goes to 400 centimeters in 10 seconds, and it's a constant velocity. So I'll plot that here. All right, let's say it's a constant velocity. Okay. So you just see, now it's going to have more data points, but I'm just trying to get to the point here on how to approach these kind of problems. So say you have some data set, you plot your data set, same kind of ideas before, or you look at a plotted data set, and you need to get some information from it. All right, so say it asks for the speed of the car. All right, so part A, speed of the car. And I've pretty much asked the same question multiple times, but it's very essential that we know how to get simple information from position time graphs, such as the velocity or speed of the object. So we see it goes from 0 to 400 in 10 seconds. Okay, so the average speed is going to be 400 meters. That's the distance traveled in 10 seconds. Okay, so that's going to be 40. Oops, I wrote meters. Whoa, what just happened? Hold on, okay, I didn't know you could do that. All right, so yeah, let me fix that. It's supposed to be meters or centimeters. Centimeters. So 400 centimeters every 10 seconds, that's 40 centimeters per second. All right, so we do in centimeters per second. Now, the reason I'm doing this is because you need to know how to do conversions. All right, so yeah, one thing, say I want to find it in meters per second. So speed in meters per second. So I got to convert. Okay, so I need to know how to do basic conversions. I'll write them up on the board, the conversion factors, just in case you forget. I don't want anyone to miss a problem just because they can't remember the conversion factor. You need to know how to use it. But stuff like there's 100 centimeters in a meter, right? We know centimeter means 10 to the negative 2. So there's 100 centimeters in a meter, or there's 1,000 meters in a kilometer, or, miles to kilometer. I'll write that conversion factor up. So being able to use the conversion factor, you got to know how to do that. So we got 100 centimeters in a meter. So if I got 40 centimeters per second, here, I'll do it the way they did in chemistry. You multiply it by your conversion factor. So I need to get rid of centimeters. I need to go into meters. So in the denominator, I'm going to have centimeters here. In the numerator, I'm going to have meters. And I know that for every 1 meter, there's 100 centimeters. Okay? Or you can do it the other way around. You can do 10 to the negative 2 meters per 1 centimeter. You get the same answer regardless. All right. So 40 over 100, 0.4 meters per second. So it's 40 centimeters per second, but it's 0.4 meters per second. All right, so being able to convert. That was an easy one. And so for the last one, let's say, so we have our data from the plot. We measured 400 centimeters over 10 seconds. Let's imagine that we measured velocity with the motion sensor and we got a different value. .1 meters per second. Okay, so whoops, it wouldn't be 4.1. That doesn't make much sense. Oh wait, what am I? Oh yeah. So 40 centimeters per second. Okay. Yeah, so I got 40 centimeters per second. I don't want to do 4.1. That doesn't make sense. That's way off. It's not going to measure 10 times the amount. I was thinking of the position, not the velocity. All right, so the velocity we got from the graph, we see it has a slope of 0.4, or say there was a line to best fit that was drawn and you saw the slope was 0.4. However it is that you got the actual data. Let's say we're measuring it in a different way. We're not measuring a bunch of data points and then getting what the experimental fit is. Let's say we use a device like a motion sensor and we get a value of 0.41. So it's not exactly the same. It's slightly off. So 0.41 meters per second. You're going to need to calculate percent error. So find the percent error. Okay. So in order to do the percent error, okay, you have your experimental value and you have your theoretical value. So the theoretical value is what it should be, and the experimental value is what you got from the experiment. Hold on one second. So in this case, all right, we have our experimental value minus what it should be over what it should be. All right, so let's say the velocity of the car should be 0.4 meters per second. All right, that's how it's calibrated. That's how it's all set up. We measured multiple data points and we got this best fit line. We got a slope of let's say 0.400. All right, we're like dead on 0.4. All right, but this thing says 0.41. All right, that's the motion sensor. Okay, so obviously it's off by a little bit, and we need to be able to calculate how much. All right, and we did that in the labs. All right, so you need to be able to do that, be able to find the percent error from experimental value versus what the theoretical value is. All right, and then you got times by 100%. That's how you do percent error. All right, so let's do the percent error of the motion detector. What was the percent error? Because we didn't get the exact same number. So we got 0.41 minus 0.4. Again, sorry about all the dotted boxes. That's just what it does. So let's say 0.40. We'll use 2 sig figs. And we divide that by 0.40. We multiply by 100%. Okay, so obviously for a problem like this, you'll have access to a calculator. I don't expect you all to be able to do this in your head. And I think the numbers on the tests are going to be, not so convenient. So I have extra calculators in the room. Just remember to bring your calculator. I'll mention it when I post this video. I'll make sure that you all have your calculator. All right, so let's do this calculation real quick. So let me pull up my calculator. All right, so we got 0.41 minus 0.4. That's 0.01 divided by 0.4. I get 0.025 times 100 because I got to express it as a percentage. I get 2.5%. That's my percent error. That's pretty good. It's not too bad. Now it's not 0, right? Because this device is not perfect. The motion sensor, there's some, what I would do is measure it multiple times to get a more precise value. But we got 0.41, so we got 2.5% off the theoretical. All right. So what would be a source of error, right? So what are some sources of error? All right. And don't just say human error, right? Because you're supposed to do it right the first time. And if you do it wrong, you're supposed to do it again. But let's say you do the measurements, you have the theoretical value of what the velocity is because you've measured multiple data points and you've drawn your best fit line. But then you just take a single measurement using some other device, right? So we use the motion sensor, we take a single measurement, and we measure what the velocity is at some point in time, okay? Well, the source of error could be... let's say the measuring device is not calibrated. Measuring device is not calibrated, right? So let's say it's off a little bit. Kind of like if you had a scale that was not zeroed, right? That could be a source of error. Or you have a scale that's slightly off, right? There's only so much precision. So you can also mention that it's within spec, right? So the device only has a certain amount of precision. Right, you can also say that. So device only has so much precision. Right, so that means that if I measure the same thing over and over and over again, I'm going to get slightly different answers. Right, so like this time it measured 0.41. Sometimes it could be 0.40 or 0.39. Right, there's a range of values that the device is going to give. Right, so the actual thing you're measuring, the object itself, that didn't change. Right, so if you do multiple measurements on the same object, like say you take a scale and you measure the same standard mass over and over and over again, and you happen to get slightly different values every time you do the measurement, well, there's some error in the device, right? And 2.5%, that's not too bad. So these are just possible sources of error. But don't put human error, right? It's not like you use the device incorrectly. You shouldn't be doing that. There's fundamental uncertainties associated with any measuring device. And if it's something like it not being calibrated, that would be a, what's it called for the different types of error? Systematic error. Okay, that would be a systematic error. Or if you have a scale, you didn't zero it in a chem lab, right? You have a scale, you're measuring weights, but you forgot to zero it, or you forgot to subtract the weight of the filter paper. Okay, well, you have to specify that, right? That'd be a systematic error. And yeah, anyways, that's pretty much it. So yeah, if you want to review these problems again, I'll see if I can make a P. Actually, that's gonna be kind of annoying. All right, just watch through the parts of the video. Like if there's a problem that doesn't really make sense, what you should do is just go over it again. Ask me a specific question in class. So like the first 5 minutes or so, I can go over any questions that people were confused about with these kind of problems, and I can clarify that before we start the test, right? We're gonna need at least 50 minutes for the test. So like after 5 minutes of questions or just last minute kind of just clarifications on certain topics or questions, we have to really get right to it. But yeah, just review everything, review your notes, review your test review that you went over before, and then hopefully by going through these problems you feel more comfortable with the FRQs that you're going to be seeing during the test. All right, so if you have any questions, just send me an email. I'm more than happy to reply. Yeah, best of luck for when you have to take the test.